So yeah, hey everybody, I'd like to introduce Hyunseung Kang from University of Wisconsin-Madison to tell us about how to deal with doing statistics and machine learning with data which is not i.i.d. And that you correlated. Well, welcome.
Yeah, well, thank you. Thank you very much for having me here today. I'm excited to, share with you all what I've been doing for the past couple of years now on doing causal inference in multi-level observational studies. So as Greg mentioned, it's essentially data that's not i.i.d. Here we're talking about a particular type of i.i.d. called multi-level observational studies and how to apply or adapt existing machine learning methods or causal inference to deal with these type of situations. So I'll just give you a brief introduction to multi-level observational studies, which is a type of non-i.i.d. data setting, and two problems that arise because it's not i.i.d. One is cluster level unmeasured confounding, and I'll talk about exactly what that means. And the second thing is obviously to deal with complex clustering structures that may happen in the multi-level observational studies. So there's a couple works that I've done in this area. I don't know if I'll have time to go over all three, so I was just going through this last night, and I think I only might have time to go through two. So the first one will be just developing machine learning estimators for treatment effects when there's cluster level unmeasured variables. So you have unmeasured variables in your data set. It's not in your data set, but it's left unmeasured. And so you want to be robust against that and to still be able to consistently estimate treatment effects in that setting. And so part one of the talk will be on that. The second part of the talk is essentially just some simple, this actually kind of came out from just working on this in general, how to retune or refit random forest methods for causal inference to deal with cluster structures, so multi-level studies. And we're going to focus on no unmeasured confounding today. There's a version for if there's unmeasured variables that exist. But yeah, here's the DOI numbers if you're interested to see later down the road. And again, just to mention, this is joint work with my student, Youmi, who's now a fifth-year PhD student here. So just a brief overview of multi-level observational studies. Observational studies, these are essentially observational studies or study units. The units that we're actually taking data from are naturally clustered or from hierarchical relationships. So the examples that we typically work with in my setting typically are clinical settings where you have patients that visit a particular hospital or clinic, but they're treated by the same provider or a set of doctors, or their patients might have similar outcome because they're treated by a similar set of doctors. Or in the case of education, which just happens more frequently, happens as well, students might be naturally clustered into schools, and these are known as two-level studies. Or students might be naturally clustered into schools, which may be naturally clustered into districts. These are known as three-level studies because there's three levels of hierarchy. Or students may belong to two non-nested groups, so they may be naturally clustered into school with the school they go to, as well as they may not be naturally clustered into which neighborhood they grew up. And that's known as a cross-classified study. So these nesting relationships don't have to be hierarchical in some nature. It can be non-nested structure. And so this type of studies, observational studies, are known as multi-level observational studies. Now, the key difference between multi-level observational studies and traditional observational studies is that the study units in the example of students are no longer i.i.d. and they have a dependence between students. So just to give you a flavor between the traditional observational studies and multi-level observational studies and what differs. So in traditional observational study, you might have seen I denote the data as O, observed data as O, and you effectively assume that OI comes from some i.i.d. distribution with some population, and I represent study units. The effective sample size, so the treating the model or training the estimates, is roughly equal to the actual sample size you actually collect at the end of the day. And this is i.i.d. data, training models for i.i.d. data been studied countless times for parametric, semi-parametric, non-parametric machine learning methods. You have the generalized linear models, generalized method of elements, M estimations, G formula, and kernel methods, causal inference, cross-value, TMLE, target minimum loss estimation, cross-fitting, and all these other variations. And key here is if there is any unmeasured variables, they're typically of one type, which is that they're individual level unmeasured confounders. So they're variables that maybe we might not be able to measure, let's say, students' prior achievement scores, and they vary with an individual, and therefore they're individual level unmeasured confounders. Now, moving on to observational studies, the biggest jump is that there's non-i.i.d. data. So typically in this world, you use double subscripts. Usually J represents some clustering structure, whether it be non-nested or some way to index those non-nested cluster structures, and I represents the units within that cluster structure. Another key difference is that the effective sample size, again, this is the sample size that that's essentially driving the variance in the standard errors, is always less than or equal to the actual number of sample size, actual number of samples that you collect. So you may actually have collected 10,000 people data from 10,000 people, but effectively you might have 8,000 people because of the clustering structure. Maybe some people are just duplicates or highly correlated with each other. Nevertheless, given these challenges, there has been countless parametric and semi-parametric methods that's been developed since the 1970s, 80s, and onwards. But there are a few non-parametric methods or even machine learning methods to deal with non-i.i.d. data. So the most famous parametric method is the generalized linear mixed effects model. This is taught typically in like an intermediate regression course. And then if you go in the econ world, you usually like the GMMs and the generalized estimating equations by Scott Seeger and co-authors. And various developments there, and the G formula from Jamie. And another thing is that if there are unmeasured variables in this data set, usually there are two types. Either you have the original individual level unmeasured variables, as well as you have some cluster level unmeasured confounders, which are essentially and I'll talk about what that means in the next 2 slides. So before I talk about that, just to give you an overview of machine learning for treatment effects, most modern, and so I listed only the modern ones here, but the most modern ones assume the data that you use to train train the machine learning effect estimators for the treatment effect is i.i.d. So perhaps the most well known is the causal forest. This assumes that the data is i.i.d. Cross-value TMLE, and originally introduced and even subsequently introduced, still assumes that data is i.i.d. Cross-fitting, which is a recent variation of a technique that was learned some time ago, also assumes the data is i.i.d. R-learner, U-learner assumes i.i.d. and there's various covariate balancing techniques, kernel-based methods by a couple people at Cornell that all assume the data is i.i.d. And now moving from i.i.d. to non-i.i.d, oftentimes people, at least in applied practice, make ad hoc adjustments to handle cluster data. So most popular, especially if there's some kind of sampling and resampling involved, is to use cluster level bootstrap, cluster level subsampling, or sample splitting, especially cross-fitting at the cluster level. And so if you look at the Causal Forest R package, they have an ad hoc way to deal with cluster data if you know what the clustering structure looks like. The other way is to use cluster level weighting, and this kind of ties with the covariate balancing weights as well, and you can try to do this as well. And there was an entire conference and challenge in 2008 dedicated to studying machine learning for treatment effects in non-i.i.d. settings. And all these methods pretty much assume that all confounders have been measured. However, in cluster level and multi-level observational data, there's another type of unmeasured confounder known as cluster level unmeasured confounder. So cluster level unmeasured confounders are unmeasured confounders that are shared between units in the same cluster. So these are effectively, so if you look at the 2-level study that I just introduced a couple of slides back, if students belong to the same school, they may share the same cluster level characteristics. Maybe the students go to the same private school or same public school. Maybe some public schools have a different emphasis on STEM than other public schools. Maybe the quality of teachers depend on the neighborhood in which these schools are actually from. There are also funding resources that may vary between school to school. There might have different after-school programs, and if you're in like a high school or middle school, secondary education, i.i.d offerings may be different. And some schools may have different compositions. Some may predominantly white or predominantly BIPOC or all boys, all girls. There's a variety here. And these variables, these characteristics are shared by every student that goes to the same school. Now, some of these cluster characteristics are measured in the data set, but others are often not. And if these cluster level characteristics jointly affect the treatment variable of interest as well as the outcome variable, and so hence an unmeasured confounder, they can definitely introduce bias in the treatment effect estimates, much like how an unmeasured individual level unmeasured confounder, if left unmeasured, introduces bias in the treatment effect estimates. Now, the case of multi-level observational data is that there's not only individual level ones, but also cluster level ones that are these unmeasured cluster level characteristics that are shared by the same people in the same cluster.
So to understand kind of the setting you're focusing on, is it more like we know these things, but we're not measuring it, like a hierarchical Bayesian like generative model? Or are these more like latent variables, which you just guess, like, I'm guessing there's 5 of them, and I have no idea what they are?
Yeah, so it could be both. So it could be latent variables that drive their clustering structure, or it could be, it could also form a hierarchical model. And like variables that are shared and that are within the same, people who are in the same hierarchy are having that same variable as well.
Do you expect to know what they might be?
Go ahead.
You expect to know what they might be, but not measure them?
Yeah, we expect to know what they might be, but not measured. Actually, for example, like you'll be surprised that the quality of teachers is not measured per school, even though
Right.
many economists, in fact, Raj Chetty believes that this is probably the single most driving factor, in addition to neighborhood in which a school is coming from, that it will affect your children's future. But yet one of them is easier to measure than the other one, and the other one is much more difficult to measure. And this, the quality of teachers, there's a latent portion of it. You know, there's no way. I mean, we can also always measure by test school achievement, test scores, but there's also the other aspects of it that might also be important as well, and that's just going to be generally difficult to measure in general.
Right. Okay, makes sense.
Yep. Alrighty. So part one of my talk will be dealing with machine learning estimates, and so how do you deal with this fact that some of these variables may not be measured or may not be very difficult to measure in real life. So first, just some notation here. So for the observed data that we get to observe, I'm going to index clusters by j as before. I is going to index the units per cluster. There's going to be a total of n units per cluster. Yij is the observed outcome of unit I in cluster j. Z represents the binary treatment of unit I in cluster j. And xij is the observed pretreatment individual level or cluster level confounders for unit I in cluster j. And we're going to also assume that there is an unmeasured pretreatment individual level cluster level confounder, but we only get to observe the first three: the outcome, the treatment, or the pretreatment observed pretreatment confounders for every study unit I in cluster J. Now, to define causal effects, we're just going to use potential outcomes model. So here, so the first one is the potential outcomes under treatment and control. So this is the outcome you would have had if you were actually treated. This is the outcome you would have had you been not treated. And essentially the target estimate of interest is the average of these two things. So it's also known as the average causal effect or the average treatment effect. And actually the paper that this work is based on goes through heterogeneous treatment effects. So not only the total population level average, but the average of this treatment effect among a subgroup of X's and how to estimate that using best linear projection methods. But we're going to, for simplicity, we're going to just talk about the average treatment effect in today's talk. So a couple causal assumptions that you need to kind of connect between the observed data and the causal, to use the observed data to estimate something causal. And these are known as causal identifying assumptions. Now, if these unmeasured variables are actually measured, then the standard assumptions to identify the causal effect, that is to estimate the causal effect but using the observed data, is as follows. So you have SUTVA, a stable unit treatment value assumption, which says that the observed value is one of the two potential outcomes depending on the treatment assignment. The second one is conditional ignorability exchangeability, where essentially it just says that the treatment variable is independent of the potential outcomes given the measured, as well as, we're pretending that these two are both measured. And then finally, positivity of overlap. Essentially, that just says that there's a probability of getting treatment and control, and that's away from 0 or 1 for every value of X and U. Now, if these three and if U, I were measured, then you can actually estimate the average causal effect or average treatment effect using the observed data that includes U. Now, if U were not measured, but only consisted of cluster level measured confounders, so if let's say Uij and Uij are the same for every person in the same cluster, actually this should be an I prime, I apologize here, then you can actually identify you can still identify the causal effect without having to measure this cluster level unmeasured confounder. And now, so before I introduce how that happens, let me first go through what the identification procedure for when Uij is measured, because that will motivate the second part when Uij is not measured, but it's cluster level. So under A1 through A3 and Uij is measured, and we can estimate the ATA of the observed data as follows. The easiest way to describe this without going through the law of total expectation 3 times is to essentially pretend that you can write a for loop between every value of X and U. This could be continuous, but just pretend for a second that you can do this. Then you will form a subgroup of units of identical X's and U's, but except it's only going to consist of the treated individuals. You form another subgroup of the individuals of identical X and U's in that for loop, but instead this is going to primarily, there's going to be all control groups. And then essentially you compute the difference in the outcome between these 1 and 2, and then denote this, define this difference in the outcome, average difference in the outcome as just tau xu. And then you go through this for loop and you average this tau hat across all this, and this average under some modeling assumption is the consistent estimate for tau. And the reason that this thing works is because essentially what you're doing at every x and u is you're comparing the only difference between the first subgroup and the second subgroup is their treatment status. Their pre-treatment variables are identical, and so therefore if there's a difference between the treated group and the control group in terms of the outcome, it must only be because of the fact that there's a difference in the treatment, because all the x's and the u's are the same. And that's why you can obtain, roughly speaking, the causal effect of treatment, at least asymptotically. Now, some modeling assumptions here. Obviously, if x is continuous and u is continuous, you can't really for loop a continuous variable. And that's where all these modeling assumptions come in. It's essentially all these, you need a modeling assumption for how to measure this mean if x, essentially how to partition the x and u space so that you can estimate the mean of the outcome within that partition. And this is typically written in the model of outcome as x and u, and then some conditional mean like this. You can also incorporate a propensity score and model for the propensity score to construct what are known as doubly robust estimators. And I'll talk about this in 3 slides.
So yes, this right now sounds very much like a causal forest, right? You cluster according to, you divide into groups according to cluster attributes, and within each grouping, you do your regular regression. Is that right? Yeah, exactly. Pretty much not just causal forest, but pretty much every causal inference problem boils down to forming 2 groups that are identical in their x's but different in their z's and just comparing their outcomes. Okay, can you just do like literally a regression is just says, take a function of your covariates, x or u, and then predict your y? Is it just boils down to that? Because that's a continuous clustering, like no clustering at all. Yeah, so you can definitely, so that's one model of doing it. So you essentially assume that you can extrapolate. Yeah, you can do a linear extrapolation if you're to do a linear model, on x and u, and then predict the mean outcome given x and u, and whether in your treated group or your control group. And so this would be estimating this value here, essentially. Okay, makes sense. Yep. Yeah, so now what if you weren't able to measure some of the variables that are important in your analysis, and you have an unmeasured confounder? So if you have an unmeasured confounder, but all these unmeasured confounders at cluster level, we can still estimate the ATE with the observed data as follows. So instead of going through all of the U's, which we don't know because we don't measure it, we actually go through the cluster indicators. So we go through each cluster and form subgroups that are identical in X in that cluster, but with the treated people in that cluster. We also do this for the subgroup of identical X's, but cluster, but with a control group. And then we just compare the differences in the outcome between these subgroups, and then denote this difference as the tau hat jx, because this is going to be computed for each cluster at a particular value of X. Then you go through this for loop, and then you average this estimate, and then this average under some modeling assumptions, a similar modeling assumptions before, is going to be a consistent estimate tau, even if we never measured the unmeasured cluster level confounder in the first place. Now, why does this work? It's similar in principle, because if you only focus on one cluster at a time, everyone has the same unmeasured confounder by the assumption that we made that all measured confounders, the UJ will only consist of primarily unmeasured cluster level confounders. And as such, when you focus on just the cluster, just going through the cluster indexes, everyone in 1 and 2 are going to have the same unmeasured confounder, even if you don't know what that unmeasured confounder is. And then essentially what then boils down to is in the previous slide where you compare between the same X and U's, to identify and estimate the treatment effect, even if UJ is unmeasured. Now, this is not new. This has been known for some time. There's been, I'm only citing the recent ones because they provide the most clear description of this. So Imai and Kim provide the DAG-based explanation of why this works. And Gelski and Imbens provide a potential outcomes explanation of why this works. However, from my knowledge, little work has been done on actually estimating this quantity. So actually doing the for loop and the modeling step involved and in a non-parametric way so that you can actually still achieve consistent estimate of tau. So let me clarify the intuition here, because I'm not quite following why you would have the same unmeasured confounder, because they could be, unless the X's predict the unmeasured confounder, I'm not sure why they would be the same. I can see that would be kind of unmeasured confounder values might be like i.i.d. or something, but why would they be the same within each cluster?
Yeah, so if you think about the school example, let's say you forgot to measure quality of teachers, but if I were to just look at one school, school A, then I know that everyone in that school presumably is going to have, let's say in a classroom, just to be simple, is going to have the same quality of teacher variable uj, even though I actually never measured that thing.
Okay, so the idea is that whatever the unmeasured confounder is, it's determined by the measured unit confounders.
Yeah, it's actually determined by which cluster you belong to. Because by knowing that you belong to cluster A or cluster B or cluster C or cluster 1, I know everyone in that cluster has to have the same cluster level unmeasured confounder. Now, there's going to be a difference in the individual level unmeasured confounder. So even if you're in the same classroom, even if you're in the same classroom with the same teacher, you might have different, backgrounds, from family backgrounds, but all of you share the same unmeasured confounder, which may be in that case, like let's say a quality of teacher in that classroom.
Okay, so now it sounds like, okay, for one thing, if you do standard causal graph analysis, you will pick up that those confounders are causally related, even though they're mediated by some unmeasured confounder, like teacher quality. So I guess in this case would be your town is causally driving your test outcomes, but the fact that it's mediated by teacher quality is not measured, but irrelevant for this analysis.
I wouldn't call it a mediation, but yeah, I mean, essentially, in some sense, yeah, there's a measured variable that's essentially kind of conditions away all the unmeasured cluster level variables to some degree. It's not a mediator in a sense that the treatment effect is moderating or changing the value of the unmeasured confounder necessarily, but but yeah, roughly, if you think about a graphical model, essentially what is happening here is by knowing that you go to school A, then essentially this conditions away all the unmeasured variables that's associated, that describes school A.
And now David's question is, are you going to have very tiny clusters if you have to deal with so many different individual confounders?
Yeah, so essentially this is a good question. So we noticed that at least in our practical exam, or to the best of our ability to tune machine learning method, usually the cluster size should be bigger than 5 individuals, and tend to get very good performance, but 5 should be the minimum.
Okay.
But again, this might just be due to our lack of training and tuning these very fancy. We'll talk about the methods that we tune.
That'd be good, yeah.
But yeah, that's what we currently recommend.
Got
and
it.
so,
Thanks.
Yep, no problem.
Poor kids, poor schools that are worse teachers, that affect us.
Sir, can you repeat your question again? I wasn't able to hear it.
These are kind of correlated with use.
I think this is correlated use. Is that the question?
So correlated. So suppose poor kids tend to get worse teachers.
Yeah, I'm not sure the sound quality is pretty bad from you, Ching.
Oh, okay.
If you want to type it in, that would help.
Oh, never mind. I'll do that later. Yeah.
Oh, cool. Thanks.
Okay. Okay. So then, yeah. So given this identification, but we don't know a good non-parametric estimator for this, we propose 3 ways to do this. All of them begin with existing methods and just tweaking it to make it work. So the first one is what's known as the W-robust estimator. So if we had observed U, there's this estimator called the W-robust. Well, there are many estimators that are W-robust, but there's this one particular estimator that's W-robust. And essentially, it's a deform. You just sum over tau ij's for every individual. So this should be little n. And then this tau ij essentially has this particular form. So you have the outcome, the treatment variable, you have the propensity score, and you have that regression, the model for the outcome, mean outcome given x and u. And then you have the same kind of variation flavor here. Now, one of the nice things about this type of estimator is that it's consistent as long as either the outcome model or the propensity score is correctly specified, but not necessarily both. That means you can misspecify and you can completely be off in how you model this M1 function or M0 function. As long as you model the propensity score correctly, it will still be a consistent estimate of the treatment effect, and vice versa. If you, let's say, screwed up modeling the propensity score, but was great at modeling the M1 and M0, then you will still be a consistent estimate tau hat. Now, if you're lucky and got both of these things modeled correctly, then this would be the most efficient, the best estimator possible in terms of semi-parametric coefficient. That is, it's going to squeeze out the most juice in your data in terms of minimizing variance. Now, recent work in the machine learning world, and especially for estimating treatment effects, has essentially replaced the outcome regression portion and the propensity score portion, which is, if you look at this, this is just essentially a supervised learning problem, into just very kernels, SVMs, neural nets, and what have you, or even like bagged estimates, or there's a range of estimates that you can just simply plug in, just to, so that we can best model the propensity score and the outcome regression model. However, to even run this thing, you need to know what UJ is. To train this supervised learning problem, you observe X, but if you don't observe U, then there's no way to actually train this model properly. So in our case, where UJ is not measured, but let's say there's a cluster, and again, sorry for the UJ, the key idea is that this unmeasured confounder can be actually written as a function of the observed data, and this can be shown fairly easily if you define this new variable dij, which denotes a dummy variable for cluster membership with the unit I and j. So essentially, it's going to be a vector of length number of clusters, and then at the entry at the jth entry, you're going to have a 1 because this should be jth entry. Because that person belongs to cluster J. Key observation here is that every unmeasured confounder, uj, can be written as a linear function of dij. So what I mean by this is that every unmeasured variable, that cluster level variable, is essentially just a linear functional of dij multiplied by this gamma. And gamma is unknown, and hence we don't know what this uij is. But the key property here is that there's a linear relationship between this thing, or this linear relationship is governed by some unknown parameter gamma. Now, based on this fact, then what we can do is we can take the original outcome model or the propensity score model as written, and then just plug in this expression here. And then what you get in this second line here is that this effectively just becomes a machine supervised learning problem where you're trying to predict y based on x, d, and z, and this gamma can be treated as an unmeasured unknown parameter in your supervised learning model. Similarly, for the propensity score, once you replace this uij of gamma, essentially what becomes is you have a function of x, d, and then this gamma can be kind of absorbed as like an unmeasured parameter in your supervised learning model. And then we can just essentially estimate, these are known as what we call proxy regressions because they're proxies of the unmeasured variable using the observed variable d. And we can just use very fancy machine learning methods to estimate these things to get a proxy estimate of the regression, the conditional expectation given the unmeasured variable. So just to illustrate how this works, just as an example, suppose there are only 2 clusters, there are no measured covariates, but there is an unmeasured covariate cluster level confounder, let's say school funding level from 1 to 10, 10 being great, 1 being not so great. For the first cluster, suppose I'm flipping the I and j, sorry. The cluster level unmeasured confounder is uj2, and the cluster 2, the cluster level measured confounder is uj4. By the key fact, we have the uj, even though we don't observe these 2 and 4s, we know that 2 and 4 must come from a linear functional d, or this gamma, again, we don't observe this, is 2 and 4. Now, our goal is to replace this thing that came out in the doubly robust estimator with something that we can measure. And for example purpose, let's say this is actually the true model for this is linear. Again, we won't be able to train this model because we never observed uj. However, because we know this property, that uj has to equal to some gamma d, suppose we have a proxy regression that uses d, and if you write out this proxy regression, and we're going to use a linear regression to estimate this proxy regression, this is going to have a sum from alpha 0 plus alpha 1 dj. But based on the relationship between u and d, you actually know that this alpha has to be a multiple of d beta 1 gamma. And essentially, by training this model, M1, we can actually directly train on this M1 uj. And that's the key idea here, essentially, is that if both of them, as long as we have a complex model for proxy regressions that encapsulates whatever the observed outcome model is, we can effectively estimate this original outcome model depending on the unmeasured variable with something that's measured. All right, and so this is our estimator of the treatment effect based on proxy regression. Is essentially you replace all the m's and the e's, if that's with the unknown variable, with the dummy variables that indicate what your cluster membership is, and then you just kind of run this exercise through. And we call this estimator the PR estimator for short because it's based on proxy regression. Now, the second method is essentially extending the recent estimator called the DRCGE estimator. Essentially, this is an estimator that also deals with the same setting. You have a non-i.i.d. data, but they're clustered in some way, and then they propose a semi-parametric estimator to estimate the treatment effect in that setting. And what they do is they propose two models. Essentially, there's semi-parametric because you can see that there's a parametric component and there's a semi-parametric component where these are just some arbitrary functions. You have a model for y given zxu is based on some non-parametric function as well as a parametric proportion. And then you have the propensity score essentially depending on two unknown functionals. In the original work, Zetterquist actually assumed that Gx and Hx are parametric. So the only non-parametric portion was how the unmeasured confounder affects the outcome or the treatment effect. And then they actually proposed a doubly robust estimator for the beta, which you can actually rewrite this as the treatment effect tau under some very mild assumptions. And you can, again, once, let's say we were able to estimate Gx and Hx by some measure, we could just solve this estimating equation form. Now, this thing looks very complicated, and initially this is how they wrote it, but then I realized when I was working on this, it's essentially just an i.i.d. regression problem, where you take this variable as the instruments, this variable as the endogenous variable, and this variable is the outcome, and you just put it into your favorite i.i.d. regression package, and now estimate beta, and then there's a formula in their paper that translates the beta into the treatment effect tau. Now, our extension to this is essentially to allow Gx and Hx to be non-parametric, and there are two ways to do this. One, I think, is useful for people who know how to tweak machine learning methods, and the other one is more useful for applied people who don't know the in and outs of the machine learning method. So the first one is to actually use a loss function, new loss function that is robust to cluster level unmeasured confounders. So one of the new loss functions that we propose is this particular loss function. So we're going to estimate this H function based on this loss, and it's a special type of loss. Essentially, it's not exactly like a, there's an outcome and there's some functional here. It's an outcome minus some functional minus this centering factor, actually, that's critical. And then we're going to also estimate this Gx portion and as well as this beta portion jointly by solving this thing. Again, it looks like your usual least squares loss where the outcome is here and then some functional here, but we actually have this centering operator, and the centering operator makes this thing robust to cluster level unmeasured confounding. And again, this is a variation of this has been talked about in these previous works in the context of kernels, but you can actually generalize this observation to just realize that all you need is a loss function of this particular type and then just train this model based on this loss function. Now, the other approach, if you cannot change the internal loss function or don't know how to solve this loss function for some functional class and some gradient, you can actually just, and if you only have existing ML methods or packages, and the loss function, the initial loss function for this is a squared error loss, then one way to kind of hack your way through this is to essentially use the xij star, x bar, and then zij star as the outcome regression predictors, and yij is the response. So essentially, this portion can somehow effectively be approximated by this thing, although it's not a perfect approximation, but it can be reasonably approximated. And the same thing for this portion. You can effectively estimate, kind of mimic this portion as a function of these two predictors. So you can just plug it into your favorite existing ML method with a squared error loss, and then get an estimate of H hat x and G hat x that are similar to. Yeah, and once H and Gx are estimated, then you use the previous equation or the i.i.d. regression to re-estimate beta, and then re-estimate the beta to translate into estimate of the tau. The third method is just combining the two methods. So if you recall, the previous method, the second method assumed that the G and X are separable, that there is a function for Gx and there's a function for Gu. Now we just assume that this thing is completely non-separable, and we have some function here. We still assume a parametric component. And then the same thing here, we just assume that this is non-separable. And then based on what we learned from proxy regression, where we can replace this uj by an observable d, we essentially use a proxy regression to estimate this thing and then estimate beta using the trick data from method 2. And we call this the DDPR. Alrighty, so some simulation studies just to numerically demonstrate that this thing works. On the left is the 2-level study. So you have a student at the individual level and the school at the top level. And the cross-classified is essentially you have students that belong either to one neighborhood, a non-nested structure. So you have some school, the student may go to the same school, but the student may belong to a different neighborhood group. And here, the first 3 are our estimators, the proxy regression, the double demeaning, the one where we essentially use the different loss function, and the DDPR, which combines the 2. The true treatment effect is 3, and notice bias, SD, and RMSE are written for numerical purposes. These are the existing ones. So this is the one that used the parametric model. These are SPART and TMLE. So these are machine learning models as applied directly outside the box to multi-level observational data. Clearly, if you just do this naively, it's going to be biased, whereas if you use our corrections, especially for unmeasured level confounding, it's essentially consistent. The same happens for cross-classified studies. With more complicated clustering structures, our estimators are much more closer to the truth than these ones, especially if you look at the tailing behavior of this, it's fairly large, and you can see that the bias and the variance is also much more inflated compared to our adjustments here, especially DD and DDPR. We also did some real data analysis. I'm just looking at the time to make sure that I have enough time for the second one. So there's a very famous longitudinal study that's still ongoing that some of your children might be participating, which is essentially the US government keeps track of how kindergartners perform throughout their course of from primary all the way to secondary school for some set of schools, for some set of students. And this is some subset of that. So we have 2,496 students from 164 schools. We're going to measure their math achievement scores at the near 8th grade based on what and the causal effect of essentially whether taking an algebra class or high-level math class in the beginning of 8th grade affects math achievement scores. Obviously, if you went through middle school in the U.S., this is probably highly causal because people who are interested in taking higher-level algebra, algebra, high-level math classes, are more likely to be interested in math and more likely to do well in math just because they're volunteering to take high-level courses. Some covariates that were measured in this study, some individual level covariates that describe the students, so they actually measured the student prior scores. This goes back all the way to elementary school. Socioeconomic status, poverty level, mom's education, gender, race, family type, expected degree. Expected degrees like what is expected from the student based on their parents' what does the parent expect their child to do in high school, whether they actually get the high school degree or not. So there's some cluster level covariates as well. School type, private, public. It divides into magnet, rural, inner city, and a couple more variations. For private, it divides into non-denominational, denominational, and within the denominational, there becomes all boys, all girls, and there's a couple more in that category. Location, where the school is, and the region, and region usually tying with district. Unfortunately, if you notice this, and this is a very large data set, teacher quality was not measured, and it's still a hard thing to measure here. We only know roughly that neighborhood definitely matters, but we don't know. I mean, you could live in a very fancy neighborhood, but if you have a terrible teacher, then it's the education might not be as worth it as if you live in a poor neighborhood but have a very very nice set of teachers. Then it can make a difference as well. So some of these that we'll measure with school funding, after school programs, STEM emphasis, and other things. And so this could definitely bias the causal effect estimate from Z to Y. And this is just your usual differences between the treatment and control groups without any adjustments. So if you just look at the descriptive statistics, control group are students who did not take algebra or high-level math courses. Treated group are the students who took the algebra high-level math courses. You notice that students in the control group are mostly from the rural areas and small town in the South, and students in the treated group, so those students are taking the algebra courses, they tend to be from city areas outside of the South as well. Also, if you notice the treated group of students who are taking the higher level algebra, high level courses, they tend to have a higher achievement score, higher as in they already did well in their classes. So there's a big difference here, and the goal of our exercise is not only adjust for this but also adjust for the school level covariates, and as well as adjust for school level covariate difference in the school level covariates that we weren't able to measure, notably a teacher quality within school. And indeed, if you just do the difference in means, you get that the treatment effect is ginormous. And once you adjust for confounding, our estimates say that there is indeed a causal effect and it's significant. Surprisingly, also the BART and TMLE and DRCGE also actually says that there is a treatment effect and the magnitude is similar between the two. Probably my guess is that it's either the case that there's not too much cluster level unmeasured confounding, and it may be already be driven by prior achievement scores, and maybe this region already kind of captures some aspects of teacher quality. But in any case, our method, regardless of, is robust in the sense that we don't have to worry about whether we actually measured or did not measure the cluster level covariate at the end of the day. Our method will still remain consistent regardless. Alrighty, so in the next 5 or 10 minutes-ish that I have, I'll just discuss some things that we learned through another separate project, a smallish project that we learned about how to better tune machine learning estimators to work with multi-level studies or non-i.i.d. studies. And these are by no means theoretical. These are essentially, we were just frustrated by the fact that there weren't many machine learning technique, or there weren't many good set of guidelines on practical set of guidelines, how to actually retune or refit machine learning methods. And here we'll just focus on random forest because this one is the one that we understand the most. And the goal here is to essentially, how do you refit random forest so that they can better understand the multi-level structure underlying the data set. So we'll focus on causal forest. This is the most famous one for as an example. Just as a brief overview of causal forest, how does this thing work? Effectively, the first step is to estimate this honest versions of this supervised learning problem and the propensity score. And then after this, it computes essentially this formula here. If you notice, this is essentially a weighted linear regression where this portion in the bracket is the predictor and this portion in the bracket is the outcome. And the weights are essentially, you put in the weights as alpha ij. And you can run LM on this thing as the predictor, this thing as the outcome of the weights as this thing, and it'll literally compute this tau hat x as well. And these weights are essentially adaptive weights, so they essentially tell you how much each observation has an influence on the final treatment effect estimate. And these weights are computed by a fairly complicated algorithm based on subsampling and recursive partitioning within that subsample. And then once you get estimates of tau x for every you can average this for observed values of x to get the estimate of tau. And so this is roughly causal forest in a nutshell. Unfortunately, this method was initially developed for i.i.d. data. Since it's a publication and since there have been many updates to this, and because a lot of people deal with cluster data, there have been ad hoc adjustments made to this, some of which we actually recommended in the GRF package. And you can see the recent updates on GRF package on how they deal with cluster data. And so we wanted to figure out, is there a way to provide simple adjustments to this procedure so that it better leverages the multi-level structure? It may not be perfect because there's multi-level structure can be complicated, but it should be better than the existing over the shelf, just naively applying this to multi-level data. So we consider 3 simple retuning strategies. One is to actually replace the internal estimates of the propensity score by a generalized linear mixed effects model. And so this is a parametric model, and this is a common model used in the practice to account for clustering in multi-level observation studies. And the reason that we chose to model the propensity score by a parametric form is because, unlike the outcome, which may be continuous, for the treatment, if it's binary, there's less variation that can be expected here. And so essentially, even if you use the most fanciest model possible to do this, how it differs to logistic regression is not going to be big, because the range in which this differs is between 0 and 1. And by positivity, this is going to be bounded between 0 and 1. So we're not going to be off by too much. And so that's why we decided to actually just use the parametric form. And instead, by using the parametric form, we can actually leverage the mixed effects models to account for clustering structure. And here we literally use the most simplest possible, which is a logistic mixed effect model with random effect terms to model this particular portion. The second thing that we tried is to simply model the cluster membership as part as part of the xi. So this is essentially replacing the dij that I talked about as part of the predictor space, and then letting causal force figure this out, that there is a clustering structure and that there, you should account for this clustering structure. And the third one is just to take the combine two approaches. We tried a whole host of other things that's not in the paper, but these are the two that would be the most obvious for people who are working in multi-level observational data. And these, one of them, especially this one, showed the best performance actually. So here's some simulation results just to show this. So on the blue is the parametric method. So these are already existing parametric methods. They're going to be great if the model is correctly specified. The green one is the causal force naively applied. So this is just out of the shell, just dump it into the data and see what the estimates look like. And these are our modifications. The first one is essentially using the mixed effects propensity score model. This is using the dij as the part of the predictors, and this is the combined approach. If you look at it unmodified, if you just naively apply causal force to cluster data, it is going to be a higher bias. And this makes sense because it was initially designed for i.i.d. data. If you apply our correction just by adding a parametric propensity score, mixed effects propensity score, the bias decreases by 2%, and in some cases 3%. And we can make this dramatic as well if you wanted to. Actually, the editor initially was 10 to 1%, but the editor was like, the simulation model looks too exaggerated, so we tailored it down a little bit to what the data might look like at the end of the day. And so there is definitely a difference. By just doing a very simple adjustment, we can definitely reduce the variance. Also, we can reduce the MSE too, as well as variance by a lot. And here, the parametric methods perform reasonably well, partly because, except for this one, MMWS, partly because all the models are correctly specified. Now, this is a more complicated model where we vary a lot of things. So, we have a student in a school level as a school as 2 level, but we could also modify the type of cluster. So some clusters could have 2 students, other clusters have hundreds of students. And if you vary this around a lot, you could get different combinations of clustering. And so each of these panels represent one variation of that. Again, the blue represents the parametric methods, that the green represents the naive causal force that's applied, unmodified causal force that's applied, and the red ones are our modifications. I didn't circle all this, but you can probably tell that the modified ones do better in most cases than the non-modified ones, especially in this region. Once you get into this region, it tends to perform not as well, but it's not as worse as the other ones as well. So this is just to illustrate that these heuristics aren't perfect. They're simple for a reason, but even if they're not perfect, they're not worse. They're not as bad as we initially thought it would be. In fact, their MSEs are sometimes actually less than this one, which was interesting to me. And roughly speaking, if you look at the ordering of the bias, is that parametric methods incorrectly specified will be greater than the unmodified CS, which will be has a higher bias than the bias from our modified CS as well. This also works with 3-level data, cross-classified data. Here, I just present 3-level data just to have variation. Again, unmodified ones have a higher bias compared to just a simple modification. It might not be a lot in some metrics, but given the fact that it only requires just replacing the internal propensity score model with just the parametric GLLM, we think this is a simple heuristic that could definitely improve the performance of existing estimators. Yeah, so some takeaways from this exercise that we've done. We think, as our general recommendation, whenever you apply machine learning methods to multi-level observational data, we believe the simplest solution, maybe not the theoretically correct solution, but the simplest solution, the first step solution, is to essentially replace the propensity score estimates of something, we use GLLMs, or something parametric and that parametric model encapsulates the clustering structure. And because a lot of these machine learning methods, at least the modern ones, are doubly robust, outcome regression kind of has a second shot at it. And the parametric propensity score, even if it's grossly misspecified, it's strictly bounded between 0 and 1. So the bias isn't as big as one may seem, at least in practice. The other thing that we learned, and I didn't show this here, I didn't talk about it in detail here, is that using cluster level indicators or DIJ directly as plugins, as predictors, is a bad idea. It has high bias, and they're only appropriate if there are very few clusters, but the clusters are very large in size. And obviously, parametric methods just generally don't perform well if there is if the models are misspecified. Yeah, so this is just a summary of the presentation. So we just discussed today about multi-level observational studies and some challenges that presents for machine learning methods. The first one being that there are new types of unmeasured variables known as cluster level unmeasured variables that are shared between the same people in the same cluster. And just the second thing is generally retooling, refitting existing ML methods or i.i.d. data to account for clustering structure. The part one of the talk talked about different ways to deal with unmeasured cluster level variables by using these different variations, PR, DD, and DDPR. And part two proposed some simple heuristics to modify at least the random forest methods to initially design for i.i.d. data to multi-level settings. And the big takeaway there is that, again, these are heuristics. They're not, I don't think they're theoretically correct, but these very simple heuristics tend to work very well, as at least first step approximations to better leverage the clustering structure information in the data set. And with that, yeah, thank you again for your attention. I'll take questions.
Cool. Yeah, thank you very much. Are there questions? So I have one. I want to get like the nugget of kind of the key intuition. I think, tell me if I got this right. It seems like the main problem with if you don't actually know the cluster membership or the unmeasured, like the hierarchy, you have the indicators, like the unit level attributes which predict it. But if you don't know what the teacher quality or whatever is, you're going to misweight them. If you have 50,000 good teachers and 10,000 bad teachers, you will kind of weight the good teachers way more without knowing it, right? And all your techniques essentially infer what those might be and kind of reweight them. Like if you were going to do inverse probability metric, inverse probabilities, but you can't do that here. This is your hack to get that, right?
Yeah, exactly. So if in that example of like 50,000 great teachers and 10,000 bad teachers, asymptotically this problem will go away. But yeah, in finite sample, what you're going to have is you might misweigh them, but what the method ultimately is trying to do is to essentially weigh them properly weigh them to their true population proportion so that you get a consistent estimated treatment effect.
Right. And like in one part, you assume that the mapping was linear, which kind of helped you out. But do you generally, first of all, is that right? Like assuming a simpler mapping between like the unit level attributes and the cluster level attributes, that seems to simplify the problem, right?
Actually, that linear mapping holds irrespective of what the unmeasured confounder is. So it's always going to be linear form. And so that's what we prove in the paper, is that it's not an assumption. It's actually, we prove that every unmeasured cluster level confounder has to have a linear form in terms of these indicators, essentially, and that's the key observation, is that people, at least based on again, this literature is very dense in the social science world, so I haven't read every social science paper, but what we discovered is that essentially every unmeasured cluster level confounder can be written in a linear form, and that's effectively what helps us a lot, actually.
Maybe I'm not following. It seems like there has to be a way to break that, right? Like in the sense that I can come up with some really complicated dynamics, that really drives the system, and my indicator is like some simple reduction of that dynamics. I bet you that's not going to be linear as a function of my personal indicator.
I mean, so if you're thinking like in the case where your unmeasured variables are growing in dimension, then I agree with you. But if you're thinking like these unmeasured variables are not like just some fixed dimension and we don't know what that dimension is, then essentially you can think of this as a basis expansion because the dimension of this unmeasured variable is fixed, and then we're essentially taking these are shared between the same individual, same people in the cluster. effectively, you can do a basis expansion on this space of D, and then it's just a linear combination of this basis expansion vector. Now, I agree with you. If the unmeasured cluster level variable is growing in dimension as sample size increases, then yeah, this approximation will likely fail, actually. But
so here's an example. Maybe you can explain to me what the intuition I'm missing. If my unit level attribute is my income, right? And then the hidden thing is the interest rate I can get because of my income, because I have a good credit score. The interest rate is roughly speaking, log of my income. I mean, it's not quite that, but it would be probably a linear function of the log of my income. But it's not linear anymore because it's the log of my income.
Right, but those are individual level covariates, right? They're not shared between They're not shared between.
Okay, fine. It's the interest rates charged by banks in my area. That's a bit fake because they're actually national interest rates. But if you go back far enough, there would have been the case where each town has its own interest rate. I'm sure we'll have other things which are fundamentally rates, not numbers which are local. So if you have the hidden confounder is the rate of my town.
Yeah, then you can predict that hidden confounder by essentially looking at which town you live in, and it'll be a linear combination of the towns in that area. So we might not be able to predict your actual individual premiums, whatever that may be, but we can predict. We can write a function. The neighborhood or the bank level interest rate, which may be hidden, can be predicted essentially by a linear combination of which bank you which bank you do your business with, or which neighborhood in which that interest rate applies to.
So it sounds like you're assuming you're going to have indicator variables of towns, like the binary things that say this town, this town, this town, right?
Yeah, exactly. That's what this D is.
It's a linear function. Got it. It's a linear function of the indicator variables.
Yes, exactly. That's correct.
All right. Well, that makes sense then.
Yeah, that's correct.
Yeah,
and good. Key observation. Yeah.
Well, cool. Thank you very much. It was fantastic.
Yeah, thank you for having me. It was nice to just reorganize my thoughts on this and then just to share what we've been doing on this area.
Cool.